Okay, so welcome back, and now we're going to start talking about derivatives as rates of change. So one of the things that we can use derivatives for is when we want to know the amount of change in the y value over a certain interval in the x value. Okay, so for example, as we've seen before, that if we have an interval that we're interested in, we can find the amount of change in f of x over that interval if we know the function, the value of the function at a point, and the rate of change of the function at that point, at the given point. So what we're interested in is we want to find the amount of change, right, in the y value. Well, what we found is over an interval, we would say that the amount of change can be represented by f of x, or a, I would say a since we're given a particular value, a plus h, right, minus f of a, right? So that is what we use to denote an amount of change, right? We've seen this before at a particular point. Okay. Now, so that's how we get the amount of change over the interval. Now, the average amount of change is when we take this and we divide by the distance away from the point. So that would be h, right? H is that horizontal distance. And so this formula, as we know from previous discussions, is what we call the average amount of change. Okay? And now, what can we use this for? Well, if we have an interval, this would represent the amount of change, okay? It's the ratio of the amount of change over the interval to the corresponding change in x values, which is denoted by h. And so now we know already that if we take the limit of this thing as h approaches 0, that's going to give us instantaneous rate of change, right? So if we take the limit as h approaches 0, that's going to give us instantaneous velocity, which is the derivative f prime of a, right? It'll also give us the slope, right? The instantaneous rate of change in the function, or the slope function, or the actual slope at the point A, right? So in this case, it's going to give us the slope. So now, but if we take small enough values, right? So this says, hey, as h goes to 0, but if we take small values of h, then we can approximate the value of the function at another point by using this, right? So we can say f prime of a is approximately equal to f of a plus h minus f of a over h. Okay, so again, assuming that we're taking small enough values of h, this is going to be a good approximation. And then what we can do is we can solve for f of a minus h. So this would represent the y value of another point that is h away from a in the x direction. Okay, on the x-axis, right? So we could then say that f of a plus h is going to be approximately equal to what? It'd be f of a plus h times f prime of a. And so we get an approximation that is based on just f of a, right? So we have the starting point, the given point, and the h, right? How far away you're going to go from a, and the derivative, the slope, the instantaneous rate of change. Okay, so why is this important, or what can we do with this? Well, first, again, we could use the formula if we only know f of a and f prime of a, and which we want to estimate the value of f of a plus h for some given distance h from a. Okay? So, for example, we may want to use this to use in a current population of a city. So let's say we have a current population in a city, and we want to use this formula to approximate the population of the city within a certain date in the future. Obviously, we can't go too far away, but in the near future, let's say we want to estimate the population of the city in the near future, we could do that using this approximation. Now, keep in mind that this is why I have this illustration. So here's our point. We want to estimate this f of a plus h, right? So here we are. So here's our distance, h, right? So we want to approximate this y value here. Now we're going to use this equation, right? Because really what we're doing is we're using the equation of a line, right? In fact, we're taking this point, right? So this is like the equation of the tangent line. So our estimate is going to be based on this equation, and that's going to give us a point down here in this example. It's going to give us a point here. And notice that it's not going to be exactly the same. So this distance here is the error of estimating this point by using this formula. Okay, so there is going to be a little bit, it's an approximation, right? So there's going to be some error. But again, if we choose h small enough, the error is going to be also small. Okay, and again, when it comes to approximating population size or future population size, as long as we have a good model and we're relatively close to the point, then our prediction or forecast is going to be relatively accurate. Okay, so, but again, that's something we have to know. Okay, what else? Is there anything else I want to say about this? Nope, that's it. Okay, so that's it, and I'll see you next time, and we'll continue on. Have a good day.